It's not clear that we can have lunch here, so maybe you will have to wait till later. Okay, so okay, so let me go to the. Okay, so somehow I would like to explain how one proves this theorem. And in fact, I will give the proof in a simple case, but the idea is exactly the same. So I will begin by explaining how one can prove Faber-Kranz's theorem in the plane. Ok, so você pode me dar, que agora eu vou usar mais o quadro por tempo. Vou escrever. Ah, ótimo. Bem, então eu vou provar essa desigualdade Faber-Kranz. As ideias são essencialmente as mesmas. Tá? Então eu vou considerar um domínio no plano e a ideia okay, sorry. Okay, yeah, I have some problems with switches. Okay, so so the idea is to use the isoperimetric inequality. So what the isoperimetric inequality tells you is that if you call A of omega the area of omega, and if you call L of omega the length of the omega, then what you have always is that the length squared of omega is always bigger than or equal to 4 pi times the area. And in fact, equality holds if and only if the domain is isometric to a Euclidean ball. Well, there is another way of writing this, is by looking at a disk, which I will call omega star. And the property is that the area of omega star is the same as the area of omega. And then what the isoperimetric inequality tells you is that the length the length of the boundary of omega is always bigger than or equal to the length of the boundary of omega star. So somehow what you do, that you have one domain, and you compare this domain with a standard domain, which is the ball. Okay, and so that's the idea. So now assume that you have a function let's assume that the function takes non-negative values, and the f is 0 on the boundary. So I'm looking at the level sets of the function. So here I have some level set which corresponds to the value t plus some delta t, and here I have the level set which corresponds to the value t. And now you consider points. Let me just do something a little bigger. So you consider points and you consider the lines of gradient. Okay, so you have, let's say, point x and a point y here, and here you have a small variation of the same points. So what you can write is the following, that y minus x okay, no, f of y minus f of x. So here y is on the level set t plus delta t, and x is on the level set t. So the difference is this. On the other hand, the difference is essentially the product of the length y minus x times the gradient of f, because you are along the gradient lines. And now if you look at the variation of area, so the inside here, so what this is x minus y times delta x. And so this is, what is this? This is just delta x, delta t, divided by the gradient of f. Okay, so now you have a nice formula which tells you that you can write the measure in R2 just like this. So you consider the variables are the variable along the level lines and the variable t. And so you have what I will write the sigma x dt divided by the gradient of f. Okay, where sigma here is the measure along the level sets, which is induced by the Riemannian structure, if you want, of R2, or more generally in Rn. So you have this nice decomposition of the measure. And in particular, this tells you how you can compute functions, I mean the integral of functions. So assume you have a function from omega to r. So you have the fact that u of x dv of x is the integral from 0 to the maximum of f of the integral along the level line of u of x d sigma of x divided by the gradient of f dt. Well, of course, you have to be a little careful about the functions, but if you don't want to think too much, one thing you can do is think that f is a Morse function. And in fact, if you consider C-infinity functions, say, for example, which vanish on the boundary, that's what we will be interested in, then you can approximate these functions by Morse functions, which have only a finite number of critical values. And these values don't, I mean, and the critical points don't accumulate on the boundary. So somehow a part of something very small, you can actually write this, and you don't have to bother too much about this. Okay, so this is, we have this formula. This has a name. This is called the co-area formula. So that's a very important formula in this context. And now you can write a few things. Let me take some examples for f. The examples I will need. So the first example is to say, well, let's take U is the indicatrix of the set f bigger than some s. So it's 1 on the set of the points x at which f of x is bigger than s. So if you write the integral of omega over omega of u, so you see that this is the integral from s to the maximum of f of just of 1. And here you have, okay, so that's 1, and then you have d sigma x over the length of the gradient. Okay, so this tells you something interesting. If you call, let me call A of t now the volume of the set S, F bigger, of A of S, bigger than S, and L of S will be the perimeter, then what you have is that, so here, of course, this will be A of S, because this is exactly 1 when F is bigger than S. And so what you have is that A prime of S is the integral over, minus the integral over the level set F minus 1 of S, of d sigma over df. So that's the first interesting formula. So now you can write another formula when you take u is f squared. Okay, if you take u f squared, so here when you plug u here on the level set, the value is t squared. Okay, so here you will have a t squared. Okay, so then the integral over omega of f squared, this is if u is f squared, is the integral of t squared minus t squared a prime of t. And if you integrate by parts, if you notice that when t equals 0, and when t equals the maximum of f, this derivative will be 0, okay? And so this will give you that the integral over omega of f squared is the integral from 0 to the maximum of f of 2t a of t dt, if you just make the integration by parts. Okay? And the last formula that we will need, and I will write it here. So 3, you plug the gradient of f squared. So here you have to put the gradient of f squared, so that here you only stay with this. Okay? So now, of course, if I consider the square of the gradient and the square of the function, is because I have the Rayleigh quotient in mind. Okay, so now you have to do the usual trick that you will use Cauchy-Schwarz formula. And Cauchy-Schwarz formula tells you that, so I will write it like this: the square of the length of the level set is always less than or equal to this product okay, this is just Cauchy-Schwarz formula. And now you can work. So, well, you see, well, that's nice, because here you have this, okay? So this integral here, you find it here, and this integral here, you find it here. Up to sine. Okay? So now you are ready to... So you take any reasonable function f, which is non-negative in omega, which vanishes on the boundary, say it's a Morse function, and you look at the integral of df squared over omega. And then if you write the first formula, then you say that this is the integral from 0 to the maximum of f. And I will right away put bigger than or equal. So I have this term. Okay? And so I say that this term is bigger than the length squared divided by this other term here. So this is bigger than L squared of t divided by minus a prime of t dt. Okay, so okay, that's general computations. Okay, now I use the isoperimetric inequality. Okay, so what the isoperimetric inequality tells me is that L of t is always bigger than or equal to L star of t. Okay? So what I do is the... Okay, so what this means? This means I have... You see, you can think that you have a kind of Sugarloaf, which is the graph of your function f, and you look at what happens at 8t. And then you cut the Sugarloaf and you have some domain. Okay? And then this domain, you make a disk out of it with the same area. Okay? And now you take all these plates that you made and you put the plates one above the other on the same axis. And then what you have is this kind of Sugarloaf, but now it will be a round Sugarloaf, okay? And at each level, you will say that the length of the boundary is bigger than the length of the circle, okay? And so here you can write that this is bigger than or equal to the maximum of f, and here L star squared of t, so that's the length of the circle. And now inside, well, you have the same function, right? Just because what you do is that when you take the domains, you take the disk with the same area. So the area functions are equal. And the inequality holds only for the length. But now if you look at this, you see that this looks very much like this one, except there is a star. And so, well, you put a star here. And what do? In fact, you just say, well, now this Sugarloaf I made, this round one, this is just the graph of some function f star. And this is a function on the disk whose level sets are exactly correspond to these domains. Okay, so you have something like this, and you have your disk, and you have the level sets like this. Okay, and this one corresponds to this one here, and so on. And then you define a function f star, and this is a nice function on the disk, which vanishes on the boundary, and what you have, and this is the integral on the disk of df star squared. Okay, now if you look at equation number 2, well, what I claim is that this equation implies that the integral of f squared is equal to the integral of f star squared. Just because here you have t is t, and a of t is equal to a star of t. Okay, so 2 let me say that 2 implies that the integral of omega over omega of f squared is equal to the integral over omega star of f star squared. And now if you divide this one by this one and the second one by the second one, so you just compare the Rayleigh quotient. So what we have proved is that the Rayleigh quotient of f is always bigger than or equal to the Rayleigh quotient of f star. So what this says is that this is called the symmetrization process. And what this says is that the symmetrization process decreases the Rayleigh quotient. Okay, and now that's it. You just plug this into the min-max. Okay, because this one, you know that this is bigger than or equal to lambda 1 of omega star. And now if you take f to approximate, or say to be the first eigenfunction, then what you get, okay, so here that's a choice of f. Then here you can get the first, here you get the first eigenvalue of omega, and here by the min-max, well, not min-max, I mean that's the definition of lambda 1, you have the first eigenvalue of the disk. Okay, so what I have proved is this is a very old result. In fact, this is due to Rayleigh, and who didn't really prove it. He said it was more or less obvious. But so the result is that if you take any domain in the plane, or in Rn, in fact, if you make the symmetrization process, then the first Dirichlet eigenvalue of the domain is always bigger than or equal to the first Dirichlet eigenvalue of the ball with the same volume. Okay, in Rn. And this is just the isoperimetric inequality. And if you look carefully, then you see somehow that if you have equality, then you must have equality everywhere. And if you have equality here, for example, this will tell you that all the domains must be disks. So in fact, equality here holds if and only if omega is isometric to a disk or to a ball if I am in Rn. Okay? Okay, so the idea of this theorem is to do exactly the same thing on a manifold. But the point is that to do this, you see that there is some abstract nonsense, which is what I wrote at the beginning. It's just computation. You play with formula. And then there is one important tool, which is the isoperimetric inequality. So what we need is an isoperimetric inequality on a manifold, on a closed manifold. Okay, so I will just state the theorem. So now I will consider a closed Riemannian manifold. So let me draw a closed Riemannian manifold. And I take a domain on this manifold. Well, first thing, there is a trouble. There is a trouble because if the domain is very big, then the domain will cover the manifold, and obviously the boundary will be very small. So if you want to give an isoperimetric inequality, you have to take this into account. That's a little bit different in R2. Okay, so on a compact manifold, you have to take this into account. And the idea is to use the relative volume. So I will consider volume of omega divided by the volume of M. And then I can introduce the following function, which is the infimum of the volume, so that's if the manifold has dimension n, so that's an n minus 1 dimensional volume. That's the volume of the boundary of omega divided by the volume of M. So that's this, that's not homogeneous, okay? And this is for all omegas in M such that the volume of omega divided by the volume of M is beta. And of course here beta is between 0 and 1. So you have you consider this function on your manifold. And this function usually is called the isoperimetric profile. Essentially it describes the isoperimetric properties of your manifold. So for example, Gérard will correct me if I say a mistake. If I remember correctly, for example, if you look at the isoperimetric profile of the two-sphere, for the n-sphere that's more complicated, but for the two-sphere, if I remember correctly, the isoperimetric profile h of beta is square root of beta 1 minus beta. No? So, well, in one case, you know what the isoperimetric profile is, and usually it's not known what it looks like. Something is known, but maybe not that much. Okay, so the point now is to give an estimate from below of h of beta. Okay? And rather strangely, we have the following theorem, which tells you that you can compare the isoperimetric profile of a closed manifold to the isoperimetric profile of a sphere, whatever the sign of the curvature. But the point is that you have to adapt the radius of the sphere to the curvature and the diameter. So let me state the theorem. So maybe I will call this function hm of beta. So we have the following theorem, which is due to Besson, Gallo, and myself. And we called it the Paul-Lévy-Gromov isoperimetric inequality, essentially because this inequality was proved by Paul-Lévy in some cases, let me say, I don't remember exactly what the assumptions were, and that was proved by Gromov when the Ricci curvature is positive. Okay, and so we extended it to the general case. So okay, let me state this as follows. So assume M is a closed n-dimensional manifold, and assume that's the same notation that the infimum of the Ricci curvature times the diameter is bigger than or equal than n minus 1 than some number which we write like this to take care of the sign of the curvature and the size of the curvature. And then what the theorem tells you is that there exists some number r which can be written as a constant which depends on epsilon n and alpha, which can be computed, times the diameter, and so assume, and then hm g of beta is bigger than or equal to h, the sphere of radius r of beta. I mean, that's with the canonical metric. I mean, that's the round sphere. So what this tells you is that if you have your manifold like that, you take a domain on the manifold, then you consider the sphere with the radius r, and you take the geodesic ball here omega star such that the volume of omega star divided by the volume of the sphere is volume of omega divided by the volume of M, then the volume of the boundary of omega divided by the volume of M is always bigger than or equal to the volume of the boundary of the geodesic ball divided by the volume of the sphere. Okay, so this tells you that you compare the isoperimetric properties of the manifold M with the properties of a sphere. And the sphere is nice because that's a two-point homogeneous space. So somehow, I mean, if you think in terms of eigenfunctions, they're just looking at eigenfunctions for a ball. And so this is just an ordinary differential equation. Okay, so that's how one can prove the theorem. So now you see, if you take a closed Riemannian manifold, the first eigenvalue is 0. It's not interesting. So you take the second eigenvalue. It's strictly positive. And it must be orthogonal to the constant, so it must change sign. And if you apply Courant's theorem, it tells you that you have a domain in which it's positive and the connected domain in which it's negative. So you take the smallest, I guess, the smallest in volume of these two domains. And the second eigenvalue must be the first Dirichlet eigenvalue because the eigenfunction does not vanish in this domain. And then you apply this Fabre-Cram technique. And then you end up with a ball on the sphere. And now if you choose the biggest of the two domains, then on the sphere you will have something which is smaller than the hemisphere. And by the monotonicity theorem, you can bound from below also the first eigenfunction. It's always bigger than n if you're on the n sphere. So this is how you have this. And why you have this dm minus 2 is just because of the homogeneity here. If you look at the isoperimetric function, you can write this as probably 1 over r, the isoperimetric function of the sphere of radius 1. Okay, so by homogeneity reasons, that's why you get this term here. Okay, so that's the way of proving this. And in fact, if you remember this theorem, in fact, there is a procedure which is essentially the symmetrization for the heat kernel. So the idea to prove the theorem is to use the same isoperimetric inequality and generalize this proof of Fabre-Cram inequality to symmetrize the heat kernel. And that's how you can prove this inequality. Okay, so I am a little bit in a hurry. From this, it's very easy. I mean, you just have to sit and think a little bit. From this, it's easy to get the lower bounds in general for the eigenvalues. So of course, that's not as nice as the one for the second eigenvalue. Okay, but still you have these lower bounds, which somehow are best possible in the sense that you have the right power of J, and best possible in the sense that the assumptions are Ricci curvature bounded from below and diameter bounded from above. In Weil's formula, what you have is the volume. And as I mentioned last time, you have counterexample which show you that you cannot hope to have lower bounds using lower bound on Ricci curvature and information on the volume, for example. You need something stronger than the volume, and diameter is a reasonable thing. And then you can also have these bounds on the L infinity norms of the eigenfunctions. Okay, so that's what I wanted to say on the estimates on the eigenvalues. So So now I have to get back somewhere. Yeah, maybe here. Yeah. Right. Okay. So now I want to address a different kind of question. So far I have been interested only in the Laplacian. Yeah, he told me not to move too much, and that's very difficult to obey this kind of, you just forget it. Okay, so in fact there are, of course, a lot of very interesting geometric operators, and that's not only the Laplacian. So among the interesting operators, geometric operators, you have, for example, which I will call Jacobi operators for the, say, minimal or constant mean curvature hypersurfaces. How do these operators appear? Well, as you know, if you take a hypersurface, so assume you have a hypersurface, for example, it's, let's say it's in Rn plus 1, and you consider here a domain, and you have the normal, assume, for example, M is oriented, just to make things simpler. And now what you can do with functions with compact support, you can modify your immersion by pushing in the direction of the normal field by a certain function f, which has compact support here. And now you can look at the volume, at the derivative of the volume. So we'll put some t. So essentially you look at the compact set in your immersion, and you look how the volume changes with t, and well, so if I remember correctly, probably I will make a mistake with the sign or with I think that's something like that. So when you take the first derivative, what you find is the integral of the mean curvature against the function. Okay, I mean, if you take any field, then you will have a scalar product, but here, okay. And of course, minimal submanifolds are critical points, so h equal to 0. And now if you look at the second derivative of this functional, once you have a critical point, you want to know how the function looks like near this critical point. If you look at the second derivative, then you end up with an operator which looks like this. So with my notations, that M is a non-negative operator, the signs are like this. So if you have a minimal immersion or an immersion with a constant mean curvature of a hypersurface, assume it's orientable, then the Jacobi operator is the Laplacian plus some function which depends on the curvature. So you have the curvature of the ambient space, the Ricci curvature in the direction of the normal to the immersion, and you have also the norm squared of the second fundamental form. And so this is a very important operator in the study of minimal submanifolds. And okay, so just some definitions. So now we take a domain. So we take a domain omega here, and we are interested in the eigenvalues of the Jacobi operator in the domain omega with Dirichlet boundary conditions. Okay, so if the least eigenvalue is positive, then we say that the domain is stable. Somehow it minimizes volume or area if you're in a surface up to second order. Now, and we will say that it's weakly stable if you have only this bigger than or equal to 0. Now you also are interested in knowing if there are negative eigenvalues. I mean, you do essentially the same thing you do with geodesics. Okay, you look at the second order condition. And this is called the index. So you count the number of negative eigenvalues, and this is called the index. I mean, when omega is compact, you have only finitely many negative eigenvalues. So now the idea also is to look at increasing domains. Assume you have a complete manifold, so you look at increasing domains. So by the monotonicity principle, what you see is that the index increases. So if you take a very small domain, essentially it will be stable, because the first eigenvalue, in fact, tends to infinity when the domain shrinks. And when the domain increases, well, the first eigenvalue decreases. Maybe it will cross 0 and become a negative eigenvalue, and then you continue, and there might be finitely many or infinitely many eigenvalues crossing 0 when you increase the domain. And you look at the supremum of the index of these compact domains on the manifold, and this is called the index of the manifold. Okay, so now there is this theorem, which is a rather old result because it's due to Glasman. This is in his book on spectral theory. The proof is given in Rn, and the theorem was written for manifold by Fisher, Colbury, and Schoen in their paper on the stability of properties of minimal surfaces. So the theorem is a very general one, and it's valid in any dimension. So the theorem tells you essentially two conditions are equivalent. So the setting is that you take a complete Riemannian manifold and you have some, say, smooth function on the manifold. And you look at the operator Laplacian plus Q. So again, if you compare with the way they write the theorem, there are some minus signs around just because I take different conventions. But that's the same theorem. So now you take a compact domains and you look at the least eigenvalue in the domain with Dirichlet boundary condition for the operator Laplacian plus Q. So what the theorem tells you is that these three conditions are equivalent, that for all domains, for all relatively compact domains, the first eigenvalue is non-negative. For all domains, the first eigenvalue is strictly positive, and there exists a positive solution U on M of the equation QU, the Laplacian U plus QU equals to 0. Okay, so that's a very interesting theorem because it gives you okay, so so maybe I will let me just try to explain to you how one proves a theorem. 1 implies 2. This is very easy. This is just the monotonicity principle I explained. So when you increase, you see, if you take omega, the lambda 1 of omega is bigger than or equal to 0. Now you take omega prime bigger than omega, and still the first eigenvalue of omega prime is bigger than or equal to 0. So if omega prime is bigger, I mean there is something in the interior of the difference between the two sets, then the lambda 1 of omega, which is strictly bigger than the lambda 1 of omega prime, which is non-negative, so the first one has to be positive. Okay, so this 1 implies 2. To prove that 2 implies 3, the idea is as follows. So you take omega, say I will take a ball with radius r, and then Well, you solve in the ball. Well, this you can solve. This is because of Freldom alternative. You can solve because the first eigenvalue is positive. So this tells you that somehow the operator Laplacian plus Q is invertible with Dirichlet boundary condition. So you can solve this. And now you consider U Now you take U equals V plus 1. So if I did things right, one should have that Laplacian of U is equal to Laplacian plus Q of U is equal to 0, and U on the boundary is equal to 1. Okay, so this is not nice. So what you do now is you change things a little bit. So you will scale U differently. So you consider, in fact, U divided by U at the point x naught. Maybe I should say something before. Yeah. Okay, so you have this. So now the first thing is to say that this function U must be positive, strictly positive. So, well, if it's non-negative, then by the maximum principle, you see it must be strictly positive. Okay? So assume it takes negative values. So you have your ball like this, and you take a connected component of the set where U takes negative values. So you have some omega like this. And this omega cannot meet the boundary because U is equal to 1 on the boundary. So here U is negative. But if you take a connected component of the set where U is negative, then you see that you have this in omega, and U on the boundary of omega is equal to 0. But this is not, this implies that U must be identical to 0 in omega because of the assumption that the first eigenvalue is positive. Okay, so that implies that U in omega must be identically 0, and this is not possible because of the unique continuation property. So it tells you that U cannot take negative values. And then by the maximum principle, you conclude that U must be positive. So if U is positive, now you can take another U. So you just scale U by the value of U at x0. So now you have functions. So let me do this. Now I remember that I have my parameter R. So I have the ball, and I have the functions UR, which have the following property that they solve the equation UR at x0 is equal to 1. UR is positive. So now you have this family of functions like this. And you take R bigger and bigger. And you see, because here somehow you have some point, you get hold on the function, then the function must have a limit when R tends to infinity. Okay, so the function cannot go to 0 because you control it here. It cannot go to infinity because of Harnack inequality. Okay, so when you let R go to infinity, you have to do some work, but when R goes to infinity, this tells you that in the limit you will have a strictly positive function which solves Laplacian plus Q equal to 0. And now that 3 implies 1 or 2, the idea is you take this function U and you look at the logarithm of u, and you play a little bit. So let me just sketch the proof. I mean, that 3 implies 1. So you take u, given by 3, and you take w is the logarithm of u. And so the Laplacian of logarithm is something like that. That's because of my sign convention. Okay, so when you take the second derivative of log of u, the first derivative is u prime over u. The second derivative, you have u double prime over u minus u prime squared over u squared. And then if you take the right signs, you see that you have this. Okay? And this, of course, is something you know. That's minus q. And now the idea is to multiply this by some function with compact support in omega and to play a little bit with the formulas. And then you end up by proving that the function, you have this. You end up by proving this for any function with compact support. I mean, just using this formula, multiplying by f squared, integrating by parts, and playing a little bit with the inequalities. Okay, so you have this very nice theorem. And from this theorem, you can draw interesting conclusions. One of them, which is, I think, of independent interest, is that if you have the disk equipped with a metric which is conformal to the Euclidean metric with mu, if you call k the curvature, the Gauss curvature of the metric G, and the Laplacian of the metric G, so the relation is that 2k is the Laplacian of log of mu, then you have this property that if J is complete, then for any a bigger than or equal to 1, there is no positive solution of this equation, Laplacian plus ak times f equal to 0 on the disk. So you, okay, so this is not very hard to prove. So there is something very interesting, in fact, is that there exists some point A0, and if you look at Laplacian plus ak, then on one side of A0, the equation has positive solution, and on the other side of A0, there is no solution. So in the paper of Fischer, Colby, and Schoen, there was it was not complete. If I remember correctly, Philippe Castillon has answered the question of the optimal A0, if I remember correctly. But I think that's an interesting. Okay, so that's a corollary. So what one can do using this theorem, that one can prove this very nice result of Manfredo do Carmo and Peng, and also Fischer, Colby, and Schoen. So the proof of Fischer, Colby, and Schoen uses what I have mentioned before, that the only complete oriented stable minimal surface in R3 is the plane. So stable means that for any compact domain on the manifold, the Jacobi operator is non-negative, or strictly positive. I mean, that's the same. So, I mean, how do you do the proof? Then the idea, once you have the tools, the idea is very simple. So you have your minimal surface, you assume it's stable. So by stability and the preceding theorem, you know that there is a positive solution. Oh, yeah, sorry, I forgot to say something. If you remember what I wrote at the beginning on this subject, the Jacobi operator, the form of it, for minimal surfaces in R3, the Jacobi operator with my notations is this operator. That's the Laplacian plus twice the Gauss curvature. So if the manifold is stable, then you know that there is a positive solution to this equation. But once you know you have a positive solution to this equation, you can go to the universal cover. I mean, if you don't have the theorem, you don't know if you go to the universal cover, if the universal cover will be also stable. It's not, you cannot prove it. But if you have the theorem, then it's clear, because you have M twiddle, M R3. Here you have a positive solution of this equation, so when you come here, you also have this positive solution. Okay, and then you look at what happens, and then you know that the manifold cannot be compact, and then you look at the whether that's a disk or the plane. Well, the disk, by the preceding theorem, this is not possible. And then you just have to look at the case when this is the plane, but then you have a positive solution, and it will satisfy something like, I mean, because of the sign of k, so the function will have to be constant, so the Laplacian disappears, and you have 2k times u equals to 0 with u constant, so this means that k must be 0, and so this must be the plane. Okay, so that's the idea of the proof. In fact, they do that in a more general context. But okay, so I think I like this theorem very much. I think that's a very nice theorem, this characterization, this positivity. And so probably I won't have time to do this, but one can give a nice proof of a very old theorem of Lindelof, and look at generalizations in other contexts, using the fact that 3 implies 2, which is in fact the easy part of this theorem. Okay, so if on a domain you have a positive function such that Laplacian u plus qu equal to 0, then you know that the first eigenvalue of the domain must be positive. Okay? So I will just try to explain what Lindelof's theorem is. So that's a paper which was published in 1870 in the second volume of Mathematica Annalen. And so you do this. You have I have a symmetry problem here. So you are in R3 and you look at the catenoid. Okay, and then so you take a catenary and you rotate it about the axis. Okay, and Lindelof was interested in knowing which domains are stable on the catenoid. And you have the following construction. So we will consider rotational domains. Okay, so we'll essentially look at what happens on the catenary. Okay, so the Lindelof construction is as follows. So you take a point, and from this point, you take the tangent to the catenary, and it meets the axis at some point. And from this point, you take the second tangent to the catenary. So you have an arc here, a piece of catenary. And now you rotate this piece. And this is a maximal stable domain. Okay, so this tells you that if you take any domain contained in this one, it will be stable. And if you take any bigger domain, it will be unstable. Okay, so the proof that Lindelof gave is a very, I mean, it's elementary geometry, and you can give a proof by looking at so somehow I will rephrase it like this. If you take this point, then this point here is conjugate to this one, just like you think for geodesics. Okay? And so you can give a proof of this as follows. In fact, you have, okay, so let me write down the catenoid, but I will change okay, so in fact, I'm looking at the family of catenoids. Okay. Okay, so in fact, so you have the Jacobi operator here, and well, if you write the Jacobi operator here, okay, let me. Okay, so there is one specific one which I'm interested in, is the case when a equal to 1. In this case, at least the Jacobi operator in these coordinates, if I remember correctly, so this is cosine minus 2t dt plus 2 times cosine minus 4t, something like that. Let me just check on my notes. Yeah. Okay, so now we are working in a geometric context. And the good point in the geometric context is that you have information which comes from geometry. And there are one information essentially which comes from geometry, and it says the following. It says that if you have a killing field, I mean, this is a very general fact. I mean, I will write it just in R3 to make things simple. But if you have a killing field, and if you have a minimal immersion, then if you take the function, let me call it V sub k, the scalar product of the normal to the immersion with this killing field, then this satisfies Jacobi equation. Okay, so that's the, and now there is another fact. In the case over there, I have a family. So now you can also look at the variation of the family. Okay, so what I claim is that if I take, let's say, this one is E. If you take E, the variation of the family, scalar product with N. So again, this is, no, E. Again, this is a Jacobi field. So in fact, the reason is that when you make the computation in the second variation formula, what you see is that when you make this computation here, in fact, what you find is that when you apply this operator to this, what you find is that up to sine maybe to some constant. But you find the derivative of the mean curvature. You assume that the mean curvature is constant for all A, that for all immersions the mean curvature is constant, but it may depend on A. Okay, so when you apply this, what you find is the derivative of the mean curvature. So this explains why you find 0 here, because here the mean curvature does not depend on A. It's a deformation. It's a family of minimal surfaces, and in this case, K comes from a one-parameter group of isometries, so the family is just pushing the surface by this one-parameter group. Okay? Okay, so now if you look, I will just write the two interesting things here. So now, let's say I want to work with the catenoid. Then what I can take is I can take translations along the z-axis. And if you compute, so here this will be just ddz. So you take the vertical component of the normal vector. And what you find is that v of t is just the hyperbolic tangent of t. And here, if you compute the variation, you just have to differentiate this, and to compute the normal, then you find another function, e of t, which is 1 minus t hyperbolic tangent of t time. Okay, so if you don't believe what I said, you just plug these functions into this, the operator, and check that they are Jacobi fields. So now if you, okay, so this tells you the following. This tells you that if you take, you see this function vanishes only at t equal to 0. So what this function v being a Jacobi field tells you is already that if you look at the catenoid like this, and if you look at the upper part of the catenoid and forget the lower part, okay, so if you look at this one, then this one must be stable because this function is positive above, and of course that's the same below. Okay, so this tells you that the upper half of the catenoid must be positive. If you look at this function, then you see that this function, in fact, has only one, I mean, it's even, and it has only one positive 0. And this positive 0 exactly corresponds to the tangent here. Okay, so if you look at the tangent to the catenoid, which passes through 0, you have exactly psi 0, which satisfies 1 minus psi 0 tangent of psi 0 is equal to 0. And in fact, when you vary A, what happens is that all catenoids, they are tangent to these two lines. So in fact, these two lines are the envelope of the family of catenoids. Okay, so now how can you look at this? Well, you just think in terms of conjugate points. So you say, well, I will take some value, alpha, so let me take some value alpha. So in fact, this will be this one here, minus alpha. So you take some value alpha, and you consider the function e of alpha t, which is v of alpha e of t plus e of alpha v of t. Okay, if you look at the So just because the function e is even and the function v is odd, you see that this is 0. So now what you do is that you have just made a linear combination of two Jacobi fields. So of course this is a Jacobi field. And this Jacobi field here vanishes here. So my claim is that necessarily this Jacobi field has another 0, and this is the point here. Okay? So just forget Lindelof for a while. And the claim is that there exists a unique beta alpha such that E of alpha t beta is 0. And this must be positive. So the reason why beta alpha cannot be negative is that if I had two zeros here, you see if I had a 0 up to here even, then this would tell me that 0 is an eigenvalue for this domain, I mean for the domain generated by this part of the curve. But then increasing a little bit, I would have a negative eigenvalue. But this is not possible because I claimed that half the catenoid is stable. So why this? Okay, so the zero, the other 0 cannot be here. So hopefully, if there is one, it must be here, upside, in the upper part. Okay, so you just have to look at the functions and see that at 0, the function is positive. And if you look at what happens at infinity, just look at the form of the function, you see that it goes to minus infinity. So it must have at least a 0. And I claim that, in fact, there is only one 0 for the same reason, because I have seen that I cannot have another 0 below the axis, and I cannot have two zeros above the axis for the same reason, for the same stability reasons. Now, if you just look at the equation of the tangent, then you just see that saying that alpha, minus alpha, and beta are two zeros of this function is exactly this property of Lindelof, that the tangents meet at the axis. Okay, so now the nice thing about that is that you can generalize this property of Lindelof to other catenoids. And for example, you can do that for catenoids in the hyperbolic space, where you have a different situation. What happens in the hyperbolic space is that you have a family of catenoids, and there is a limit point, and at the right of the limit point, in fact, all the catenoids are stable. Here, in fact, the catenoid in R3, they have index 1, but in the hyperbolic space, you have catenoids which are stable. So on the right of some constant, you have stable catenoids. On the left of the constant, you have catenoids of index 1, so that's the same situation as in R3, but yet the situation is a little bit different, because if you look at the catenoids in hyperbolic space, you see here what Lindelof's theorem tells you. As I mentioned that the upper part of the catenoid is stable. But if you push a little bit below, then it becomes unstable. Okay? But that's not the same in the hyperbolic space. In fact, in the hyperbolic space, you have this situation, and you can go, either the whole catenoid is stable, and then you can go below as far as you want, or the catenoid has index 1, and you can go a little bit below 0. Okay, and in fact, well, there are two, one here and one here, and one can analyze this one. So this ZA, or minus. So if you look at this domain, then this domain is maximally stable. So if you take a bigger one, so it's symmetric, and if you increase it, then you find an unstable domain. So with this value, now if you forget what happens upstairs, so this is stable, but then you can continue to some value L of A, which is bigger than Z of A, less than Z of A, and this domain is stable. So the situation is a little bit different in the hyperbolic space. And this can be analyzed by this method I explained thoroughly. I mean, this was the fact that there are stable and unstable catenoids in H3 was discovered some time ago by Maury and, 20 years ago, or 30 years ago by Maury and later by Doccarmo and Dajcer. But they didn't really analyze the situation. And with this method, one can really understand the whole situation, and one can also give a geometric interpretation that in the hyperbolic space, the catenoids, at the beginning, when A is small, the catenoids satisfy this kind of property, like in R3. And then at some point, the catenoids, they just look like this. So the point that I mentioned, on the right of this point, you have catenoids which form a foliation, and they are stable catenoids. And on the left of this point, then you have catenoids which meet like that, and they have index 1, and this strange property. And you can prove the same thing for catenoids in H2 times R. So that's a rather general fact. So, okay. Have questions? Okay, so I have some message. Yeah, I have some message I want to. Okay, so let me go to the messages. The point is, I have some here. Let me go to here. So just okay. So first of all, just to remind you that tomorrow we will have lectures, hopefully. We will have lectures transmitted over the internet from Grenoble to here. So there will be 3 lectures. One, the titles are on the program, one on algebraic geometry, one on complex geometry, and one on arithmetic geometry. So that's all geometries, but different geometries. So the time should be 9:30, 11, and 1:30 p.m. Then on Friday, there will be 2 lectures at the Catholic University in Rio. So that's at 9:30 and 11. So I discussed, some people ask us for the notes, so I discussed with my colleagues, and we plan to revise our notes or slides, and we will put them on our web pages, and I will try to keep the links on this page I made for the event. Okay, and well, finally, I would like to thank IMPA, and in particular the staff from the support staff from computer, because we had some work for tomorrow's transmissions. So I would like really to thank them for their support. Thanks to IMPA for the hospitality here, and I would like to thank the sponsors of this event. And in particular, this is a research program which is not only mathematics, but there is a part for mathematics between our region in France, Région Rhône-Alpes, and Brazil, which is called Arcus program, and the other sponsors, in particular, CNRS, IMPA, and the Université Joseph Fourier. So that's it now.